Hello, so I'm Aleksandrs. So I might talk will complement and complements Maxim's talk, and so we'll see some common things, but we'll see something like completely different. So what I want to start with is specifics of quantum computation. So it will be somewhat similar to what Maxim just said. So if you are here, then you are interested somewhat in quantum computation, and I just listed few items that you could possibly have heard of if you are interested in this field. So one thing is quantum algorithms is a new field, so just very recent, and everyone is excited. Okay, so quantum algorithms, they don't have many applications so far. Okay, but as soon as we have quantum computer, so we'll have like a lot of applications, and so maybe we'll just use only quantum computers from some point on. So, and the last point I just said it for fun. It's more technical, so I've heard a lot, something like this, that quantum computers, how they work, they somehow can simultaneously check for exponentially many variants and choose the right one. So, somehow, I don't know how. And so what I want to show in this presentation is all these things, maybe they are somewhat true, there is some truth beneath them, they are also not so true. And so maybe I'm being too arrogant, with the saying that, okay, that they are all wrong, okay, but they are wrong at least in some sense. Okay, and for the last two, so I start with the last two, is that other applications, so maybe it's not so, it's a bit bleaker than you could hope for, that the number of applications with some, at least as it looks so far, will be quite limited. So Maxim's list is like few applications with 3, and maybe the main challenge for us theoreticians, as we are, is to get more applications and to find more problems that can be solved using quantum computers. Okay, and the last one, that quantum computers check for exponential many variants. So this is not really true. So it's somewhat true, but you really should not think about it that way. This doesn't really tell you much about how quantum works. Okay, but mostly I would like to focus on the first two points in my presentation. So this is also not so true. So first I want to claim that the quantum algorithms actually have been out there for more than 100 years. And like things like Shor's algorithms have been used in practice and with many applications. And yeah, so they have many practical applications and really instantly shaping our lives right now, even without quantum computer actually being here. Okay, so let's me move on. Okay, so 3 things I would like to really tell about quantum computation, or how it is different from usual computation. So the first thing is quantum computation is similar to using randomness. So maybe you have heard of randomized algorithms. So they use random number generators. So one specific example is, for instance, if you have a large number and you want to check whether this number is prime. So the best algorithms that are out there are used like randomness in a very essential way. Okay, and quantum is somewhat similar, but then using so-called amplitudes, they can think about it somewhat as probabilities, because like you can have different probabilities on different positions in your computation. Okay, but in this case, in quantum case, so these probabilities, they are actually called amplitudes, but I will not be using this word too much. So the probabilities can be negative, and the main thing is that they can cancel each other. So you can have a positive probability and a negative probability, whatever this means. Okay, and they cancel out, and then you get 0. And so this means that there's nothing in there. Okay, and this thing is called as destructive interference. Okay, so let me talk a bit more about this destructive interference. Okay, and okay, how it looks like. And you can actually have nice pictures what an interference is. So there is just a picture what's going on here. So it's a surface of a lake, something like this, and there are some droplets going down. So they fall, and there is like these circular waves. They start from some point, and they somewhat interfere. So they interference, and this means that one wave is added somehow to the other wave. Okay, and you get this interesting configurations of waves. So somehow they amplify each other, in some places they cancel each other. Okay, and so how does it work maybe for quantum things? This is the experiment, the famous double slit experiment from 1801, the one Maxim also talked about very briefly. Okay, it's so it's like one of the first slide of the whole thing. So the main point will be on the second slide. So it's due to Thomas Young, and so the first this slide is just about the thing that's called as diffraction of light. So if you have a light source and you have a very, very narrow slit, say in a black piece of paper, and you shine your light on it, that what happens, it doesn't go like as one slit, like one line on the wall behind it. It actually gets diffracted, so it goes out like a wave, like a circle, the same circle. Okay, and you can get some light also, like not at the center. The center gets the most light, but some light gets diffracted out to the sides. Okay, so far so good. So there's nothing really surprising here. Okay, it gets diffracted. So what? The more interesting thing happens when you have two slits. Okay, you should expect maybe that you have two slits. So you have the same pictures before, but they are added to each other. Okay, so you would have like two stripes that somewhat blur out. Okay, but that's not, so it's expectation. And so what happens in reality is that you get this very interesting zebra light pattern. So there is more light, not so much, there is a dark stripe, a white stripe, a dark stripe, a white stripe. So this is how it will look like. So if you will do this thing and take a photo of it, so it looks something like this. So there's like white stripes and black stripes between them. Okay, so why does it happen? Okay, and the short answer, it happens because of two things. One thing is that the light is actually a wave, not really a particle. And the second thing is because of the negative interference, or yes, destructive interference. Okay, so if you think about this as waves, so you can also do it like on water. You have like two sources. Okay, this is video from the double slit experiment on water. It's from Peterson, I believe. So you can also watch it online. Okay, and so if you do this, so these waves, like the circles that I had on my previous slide, so they in a way interfere with each other, and you again see in this case that really you have this these areas where you have more, so like larger waves, and there's areas where there's like nothing happens. Okay, so this is just because these waves get in some places they are amplified, and in other places they cancel out. So this is like a short description of what's going on. So you can see on the left this A and B versions. So the one of the A is these dark stripes. So this is destructive interference. So you can see there are two waves, and they are aligned so that when you have a spike on one wave, there is like an eye on the other one, so they cancel out. Okay, and you get zero there. Okay, if you just add these two plots together, you see they are like almost negation of each other. And on the second thing, it's bright area, it's constructive interference, so they amplify each other. Okay, and so this difference, so it actually depends on the difference between the lengths of these two distances from one slit and the other slit. Okay, we can calculate all the angles, so this R1 and R2, okay, and the difference depends on this angle theta, okay, and so if this their theta, their sine theta is like it's one value, then you get constructive interference. If it's another value, we get destructive interference. Okay, and we have a plot like that. So it's an explanation of how it actually looks like in nature, like this quantum effect, real quantum effect of a light being a wave. Okay, and we get this. Okay, so far so good. Okay, but the question, okay, how can you use it? Okay, so it's all very nice pictures, but really, are there any applications of this phenomenon? Okay, and I would like to give Okay, few applications that I really like, and the first one is in lenses. So lenses, objective, so you can take pictures, or you can also, it's also used there in the beamer, just right as I'm speaking, to project all these nice pictures of mine. Okay, and so the problem with the lenses, so this thing here contains many different lenses. It's like a complicated system. So built so that everything is focused and stays nice and not distracted, the front and on the edges. Okay, and the main problem is that it's built of glass or some other material that somehow diffracts this light. And you diffract in a nice way, so we get the good picture. Okay, there is a problem, though, with the refraction of light, that when you go from one medium to another medium, so one thing that we want to be happening in this lenses, in this objective, is that you go through. So you go from air to glass, or you go from glass to the air. So this is this part you want to go from left to right. But also there is also a refractive part. So also, well, say for instance, you can see also through that window, but you can also see your refraction. So these two things are happening simultaneously. Okay, and the refracted part is fundamental. So it depends on two things. It depends on this difference in materials, okay, this N1 and N2. And the second thing, it also depends on the angle how it falls out. And you can calculate everything, and it turns out that you cannot just get rid of it, you cannot just purify everything very smoothly. This thing will be there. That's because of the physics. It's because of classical physics. It gets refracted, and the problem when it gets refracted, one thing that you get a bleak picture, because this light starts traveling all through the lenses, you can't control it, and it just gets like a noise on top of your thing. Okay, this is like a fundamental problem. Okay, if you take a look from classical physics, there is no real way you can solve it. Just with that, you can do anything. But now, let's move on to the quantum effects. And what you can do, you can add another surface, very tiny. So actually the correct thing, you should be around the wavelength divided by 4. And what happens, so if you have your light going in, now there are two refractions. Okay, one refraction is from the, like this first surface, and another refraction is from the second surface. Okay, and if this is the width of this layer is the length of your wave divided by 4, then after refraction is the length of your wave divided by 2, so they exactly cancel out. So they cancel out. So this is destructive interference. It just can't go there. Although it's very counterintuitive, and this is how quantum works. So if you add another layer, somehow you get more light through, because light just cannot get refracted. It has to go through. Okay, and this is how it's done. It's really done everywhere now. On all lenses, okay, you see this rainbow style stuff on top of every lens. So this is exactly this very tiny, very narrow layer that's added to make this thing work. So this is application of a quantum effect, destructive interference in real life. Okay, and the problem is that, of course, it's not really an algorithm, but you can see that, like maybe a flavor of how you can use destructive interference. You just have to cancel the stuff that not interests you out, and then the stuff that interests you gets amplified automatically. Okay, now I would like to go to more required stuff, and so this will be a bit of the tour. So I'd like to talk about public key cryptography, and namely about RSA cryptosystem. So how many of you actually are familiar with RSA and public key? Okay, very nice. So, so I'd like to go like very short explanation of how RSA works and what is public key cryptography. So the first idea of public key crypto is how it's different from usual cryptography, which is a symmetric key, which has been out there from ancient Greeks, it's very old. That the difference in public key cryptography is that you can have two different keys. So one key is used to encrypt, and another key is used to decrypt. Okay, and in usual symmetric cryptography, that's been like known for a very long time, they are equal. So you can encrypt. If you can encrypt, you can also decrypt. So if you want to really secretly communicate, you should somehow come together, get this key, store it. Everyone stores the same key. So one key is used to encrypt, another key is used, the same key is used to decrypt. Okay, in public key cryptography, it's slightly different. That one entity that wants to get encrypted messages just generates two keys. One key is public, and one key is private. So he stores a private key. It can it's used to decrypt, and but the public key can be given to anyone. Okay, and anyone with the public key can actually encrypt a message and send it to this entity. So that's very convenient, because you do not have now to come together and agree on some common key. You can just download the public key. Okay, it's a different question how you know that's correct key. Okay, I'm not going into that now. Okay, but you can download this public key, so there is nothing secret about it. Okay, and everyone can use the same public key to encrypt. But still only the person intended to read the message can read it. Okay, and so this was a real breakthrough in cryptography, the development of public key cryptography in the 20th century. Sorry. Okay, and so as well, the first public, okay, sorry for the no pun intended, okay, public version of public key cryptography is due to these three guys, one Rivers, Eddie Stemmer, and one Edelman. Okay, it's called OSA cryptosystem because of the first letters, because this is first publicly known public key cryptosystem, still widely employed today because it's very efficient. Okay, the problem is that it's easy to break using quantum computing. Okay, so now, okay, I am first going to explain how the basics of how OSA works, and the second is how we can break it using quantum computation, quantum computers, quantum algorithms. Okay, so the first idea behind the OSA system. So now I'm starting to going just for the few slides a bit more mathematically, not just drawing pictures, but also have some formula. Okay, so the first observation, just start and write down the powers of 3. So 1, 3, 9, 27, 81, 223, all the 4, and so on. So these are all the successive powers of 3. And let's observe the last digit. Okay, it's in red. So 1, 3, 9, 7, 1, 3, 9, 7, 1, 3, 9, 7, 1, 3, 9, 7. So we can see the last digit is periodic. So it has period 4, and it gets repeated, and so on. Okay, and it turns out it's not something specific to this being the power of 3, or being this being the last digit written in decimal. It turns out that it's the same for any case. You can take any number, so in OSA it will be a product of two large primes, okay, but it's not so important for now. Okay, and you take this number, so m to the power of x modulo m, so this is the remainder of m to the power of x divided by n, and it is periodic with some period m. Okay, and again, it's also just the same thing, repeating over and over again. Okay, and two things, it's easy to find L if you know P and Q. Okay, if you know P and Q, and so P and Q are primes here, so you can easily find L. But it is very hard to find if you only know n, you know the product of 4 primes, but you do not know the individual primes. Okay, so that's the main idea actually behind the OSA cryptosystem, that you somehow, so this developer of this encryption key, who generates both private and public key, so he knows he generates two large primes, P and Q, and multiplies them together gives out n. Okay, so the trapdoor that he knows and no one else does is exactly this period L. So that's how it works. Okay, and maybe a bit more explanation of how exactly it works. So it's based on this another observation. So if you take m and take it to the power of k times L plus 1, where L is the same period as on the previous slide, then it's equal to m modulo n, so it gives the same remainder. Okay, and that's why, because for any k, so k is an integer, k times L is a multiple of period, you just get a shift by period. Okay, you get a shift by a period, so that you get the same value. Okay, and another thing, it's a bit more technical, that knowing L, this period, and some number given some number e, which is co-prime to L, okay, it's easy to find d, okay, such that e times d is equal to k times L plus 1 for some integer k. So this k L plus 1 is the same k L plus 1 as in the first point. Okay, and that's how OSA works. Okay, you take a message, and they will get the crypto text by taking n to the power of e modulo n, and you can get the message back on the crypto text by taking crypto text and taking to the power of d modulo m. So this works because c to the power of d is m to the power ed. It's equal to m to the power of kl plus 1, and it's equal to n using these two things over there. So again, the designer, he just generates this e. This is encryption key, it's public. Okay, and he can calculate this d because he knows the period and he stores it to himself. Okay, in this way he is the only person who knows d, and he is the only person who can decrypt. Although e is public, everyone can encrypt message and send it to this person, but only this designer of this cryptosystem can decode because he knows d. Okay, and okay, so that's essentially ends the explanation of how RSA works. So it was a bit technical. Okay, this might be the most technical slides of all my presentation. Okay, and so the big waypoint is two things: that how RSA is working. This is because m to the power of x is periodic. The period is only known to the designer because he knows p and q, not only n. Okay, and it turns out that we can break the system because you can use Shor's algorithm, which I am going to explain a bit how it works. So we can find the period on a quantum computer knowing only n. Okay, we can find the period, and so the period was like the sort of the thing. So it's how it works. And knowing the period, we can break the system, the RSA. Okay, so let me move on and try to explain how you can get this period finding on a quantum computer. Okay, and let me talk about salt. Okay, so salt, so everyone uses salt. It's a very nice substance. Okay, and what we know about it. Okay, on an atomic level, okay, if you maybe know, it's like it's a crystal. Okay, it has this periodic lattice, so it's chlorine and natrium. They're arranged in this interesting three-dimensional chess-like pattern. Okay, so we've been taught this in school, like each, like the salt is like a crystal, it has this thing. Okay, but the question is, okay, how do we know this? Okay, how can we really know that it looks like this? Okay, because I'm going to tell you that this thing was discovered in early 20th century by these two guys, father and son Belovs. So they got Nobel Prize for this in 1915, also coupled with a few other crystallic atomic structures. Okay, the question, how do we know this? How do we know that how do they could derive this structure? Okay, you couldn't just take a microscope and zoom in and see individual atoms. It was not possible. It's still hardly possible now. It certainly was not possible in the early 20th century. So the question, how did they do this? Okay, and the answer to this question, they used quantum algorithm. Okay, and so what did they use? They used this thing called X-ray crystallography. So X-ray is the same thing as light. The only difference is it has a very, very short wavelength, so that it actually interferes with individual atoms. Okay, and you shine this X-ray on a crystal. And so what happens, they, as before, they get it diffracted out of each atom, and they go again like in all directions. Okay, and remember that light is a wave. And exactly the same thing as in double slits happens, that for some directions you get constructive interference. So you get that your waves are aligned together and they amplify each other. But in other directions you get destructive interference. They cancel out and you see nothing there. So if you actually do this and put a photographic plate, so you see a picture, something, you just see like this weird, also somewhat periodic pattern there. Okay, and this is exactly because of this negative interference. What's happening here? Okay, and so what you another I want to say that okay, so all these atoms are very tiny. Okay, and but the thing is that they all work together because of this nice structure of this crystal, they all work together, and like each small atom like amplifies everything. So this is like you can think about a rainbow. The rainbow gets that light gets refracted from tiny spectacles of water in the air. Okay, and you do not see individual rainbows, but they all act in unison, and somehow from their combined work, you can see this beautiful picture of a rainbow. Okay, this is exactly how it's going in this diffraction picture. So you have like many atoms going in unison, and you actually see an observable thing out of this. Although, like for one atom, you would see possibly nothing. Okay, and you can cast this actually as a quantum algorithm. So we can say that the diffraction lattice is in a way Fourier transform of the atomic lattice. Okay, and just by observing this atomic lattice, the diffraction lattice, that's the thing on the left, you can deduce using the laws of quantum mechanics, like this interference things or these patterns. You can deduce what is actually the structure of the crystal itself. Okay, and this is exactly how the Shor's algorithm works. In the Shor's algorithm, you have periodic sequence, okay, and you somehow use like imaginary X-ray on it. Well, actually, it doesn't really happen in nature. It just happens like simulation digitally. Okay, but in a way, you can do it that for instance, only ones interfere with ones, like fives interfere with fives, and so on. So you can have this periodic, it's like one-dimensional periodic lattice. So it's a periodic sequence is like one-dimensional lattice. You apply a Fourier transform. You can efficiently implement Fourier transform on a quantum computer because, okay, you just saw it happens naturally, so you can believe that you can also efficiently simulate it. And you get this thing, which is also a periodic lattice. This is called a dual lattice of the first one. Yeah, and the one good thing about this, okay, it's periodic. Okay, so you would observe the points which are in black and not the points which are in white. Okay, and another thing is that it's aligned. It's okay, I should use my pointer here. It's always start in the first position. So you always first to make the zeroth position of the program. The zeroth position is always there. So it's like periodic sequence with starting with 0. So actually, what you're getting are multiples of some number. Okay, and in a way, maybe I can give some analogy. So this, as I said, this ones and fifths and 23rds, they just, we can make them interfere, just not to interfere with each other, just work individually. Okay, and they are shifts from each other. So if you take all the positions where there are ones, and then takes all positions where there are fifths, so they're just shifted by one. Okay, and this shift actually doesn't change this dual transformation. You can somehow think about this as if you take your crystal and just slightly move it in one direction, it wouldn't change the diffraction picture. Okay, because the angles that where the light goes are the same, doesn't really depend on where your crystal is. Okay, whether you shift it slightly, it's a good thing because you can locate it right after an atom. Here the same, it doesn't depend where your periodic like sequence where 7 starts from, you are still getting the same Fourier transform. Okay, and so now if you are just getting this, you can get 2 of these dots or 3 of these dots just by running it several times and just observing where it hits. Okay, you can calculate the greatest common denominator divisor of this. You can get the period of the dual lattice, like the distance, so in this case it's 4, and from that you can deduce the period of the original thing. So that's how it works. So there is not much difference between Shor's algorithm and this X-ray crystallography. That's essentially the same thing. Okay, so just one slide to compare this thing. So X-ray crystallography, and Shor's algorithm. So like the first one is analog, so you just do it. Okay, and this one is digital, so you don't really have one-dimensional periodic string hanging out there. So it's virtual. Okay, it's virtual 1D lattice, so just encode it. Okay, in crystallography it's real 3D lattice. Okay, Fourier transform is natural. In crystallography, just how the nature works. In Shor's algorithms have to implement Fourier transform, but again, as Maxim showed, so it's a quantum phenomenon, you can efficiently simulate it on a quantum computer. Okay, and the crystallography, the problem was that lattice is like the distance between these atoms is very small, so we cannot really see it. Okay, in Shor's algorithm, the problem is that this period is very, very huge, so we cannot observe it because like nothing repeats if you just take some small scale. Okay, but other than that, it's the same thing. Okay, now I just want to wrap up with some fun slides. Okay, so the serious part is over. Okay, and with fun stuff, I would like to ask you a question. So I've been asking this like for many times. Okay, and okay, so this is like maybe you couldn't expect like one correct answer to this question, but I would argue that maybe there is one answer that you would agree with me. So the question is like, which is the most popular molecule? In a way, in this case, maybe I would like to be more specific, that first you know the shape of this molecule, and the second thing, you've seen it many times, and every time you see this has a very specific connotations. So this is a tricky question maybe.
H2O?
Okay, that's a good thing, okay, but I haven't seen it very too many out there. Okay, but okay, maybe I'll just give you a hint. So, what is this building? Yes, it's okay. It's DNA. Okay, it's the new building from University of Latvia. Okay, and this has this DNA thing. Okay, and it's used in many things. So something which is savvy, technological, is somehow represented by this DNA structure. Okay, and what about this DNA stuff? So it's deoxyribonucleic acid. Okay, so it's a double helix contained of this basis TACG. Okay, and whatever. Okay, and the thing about this, okay, again, how do you know that it looks like this? It's again let's use the same thing as we thought. Okay, oh yeah, so this is another example from Singapore. Yeah, it's a bridge that's in form of a double helix. Maybe in this case it's somewhat harder to tell, unless maybe you walk through this and you see this letters DNA, you can get a hint at what it is. But it's like a DNA bridge in Singapore. Okay, again, popular stuff. What can I say? Okay, and it was used again using a quantum algorithm, like the same X-ray crystallography by Francis Crick and James Watson. And they got this Nobel Prize in medicine. Actually, it was a pure physics, I would say, but you get a Nobel Prize not even in chemistry, but in medicine, for this thing, but describing the structure of DNA. Okay, why? Because when you see the structure of DNA, you see this double helix, think, oh, that's how the stuff is copied. That's how the copy, that's how the genetic information gets from ancestors to their babies. So that's just, you just separate this double helix and then you drop over the remaining part. So that's how it's copied. Okay, and when you know that, okay, that's all the information, all the genetic information is encoded in DNA, okay, you know where to look and you know you can develop all these tools that have been used now, all this genetic stuff, just all based on this observation, obtaining this structure of this thing of DNA, and then getting this idea, okay, that's where you should look. And that's been obtained using X-ray crystallography, which is fundamentally a quantum thing, a quantum algorithm that is not, which is fundamentally the same as the Shor's algorithm, which is used to break everything. Okay, so so this is just a small, non-exhaustive list of students of Nobel Prize involving X-ray crystallography. Okay, you can see like waxing for X-ray to determine crystal structures and also helical structure of DNA from 1962, but there's also a lot of other stuff. Okay, and they're also using the same ideas. Okay, you can get a lot of Nobel Prizes, so I would suggest this is somewhat significant stuff. Right, and okay, so that's it. So thank you.